Let's try to illustrate an example of lemma about an M-augmented path in a bipartite graph. Let's consider a bipartite graph G with a vertex set L and R and matching M within this graph. Suppose the current matching M includes the edges L2, R2, L3, R3, and L6, R7. Now, suppose we find an M-augmenting path P that starts at an unmatched vertex from L, alternates between the edges not in M and edges in M, and ends at an unmatched vertex from R. Let's say the M-augmenting path P is L1, R1, R1, L2, L2, R3, R3, L5, L5, R6, and we can notice that P starts with L1, which is unmatched, and ends with R6, which is also unmatched. So just along this path, the edges L1, R1, and L5, R6 are not in set M, but R1, L2, and L2, R3 are in the M set. Let's try to construct a new matching M prime by taking the symmetric difference of M and P, which means for every edge in P that is not in M, we add it to M prime, and for every edges in P that is already in M, we remove it from M prime. Thus, the new matching M prime will be L1, R1, L3, R3, L5, R6, L6, R7. M prime now has one more edge than M, specifically the edge L5, R6, which was added, and the L2, R2 was removed since it was the part of the path P. Now, the new matching M prime is indeed a matching, and it has one more edge than M, hence cardinality of M prime is equal to cardinality of M plus 1. This is exactly what the lemma states. By repeating the process of finding M-augmenting paths and taking the symmetric difference with the current matching, we can incrementally increase the size of the matching until there's no more M-augmenting paths can be found, at which point we can have the maximum matching. Let's try to prove the process of augmenting a matching in a graph through the using of M-augmenting paths. M-augmenting path P is defined to have Q edges. Because P is an M-augmenting path, it alternates between the edges not in matching M, which is no matching edges, and the edges in matching M, which is matching edges, and starting and ending with no matching edges. So the path has the floor of Q divided by 2 matching edges, and ceiling of Q divided by 2 non-matching edges, which result in Q plus 1 vertices, since the path has one more vertex than they have edges. The vertices V1 and VQ plus 1 and endpoints of the path, and they are unmatched in M set, and the other vertices V2, V3, blah, 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 until VQ are matched in M set. The edges V1, V2, V3, V4 until VQ, VQ plus 1 are the non-matching edges, and V2, V3, V4, V5 until VQ minus 1, VQ are the matching edges. When we take the symmetric difference of M and P, we essentially removing the matching edges of P from M and adding the non-matching edges of P to M, and the result is a new set of the edges, M prime set, that includes one more non-matching edges from P than it loses in matching edges from M. So due to the alternating pattern, this means M prime has exactly one more edge than M, and thus the cardinality of M prime is equal to the cardinality of M plus 1. So the proof concludes that M prime is indeed a matching in G, and the size of the matching has been increased by 1 from M to M prime.